Good day, and welcome to Africa Teen Gigs. And today we have our digital STEM digital school. I hope that everybody is okay, and you guys are ready for another great class of physical sciences. Yes, indeed. If you have just joined in, this is a grade 11 physical sciences. Today is the 8th of July, and my name is Nonkululeko Madondo. I am indeed your physical sciences grade 11 teacher. So today we're moving on. We're still doing the chapter on electromagnetism. Okay, it's still the chapter on electromagnetism. So today we're going to be doing the Faraday's law of induction. As you guys have seen, yesterday we started out with electromagnetic induction, and we went through it and we explained so many things that I hope that if you did go through it and you were part of this classroom, you understood. And unfortunately, I had a problem with my screen and I couldn't do properly the homework. But I asked if there's people that have this Oxford Successful textbooks, they could do it. And luckily for you guys, I've got it here today. We're gonna do it. I want to make sure, guys, that whatever unit that we go through it clear with understanding and understanding how to apply the theory into questions that they ask. So no stone will be left unturned. So just reminding you once again that there's been quite a number of alterations that were made with regards to the ATPs for the caps for the 2020 syllabus that has been made by the Department of Education. And one of those adjustments was that for this chapter of electromagnetism, they have removed all the calculations. So meaning that when we work in here, we will not be doing any calculations whatsoever. We're just going to be doing the theory part, the equations. The equations are also part of the theory. Even they're just not going to ask you to calculate, for example, Coulomb's law if A, B, and C is given. So you do not have to know how to calculate, but you need to know the equations that go with each term and definition. So there's quite a lot of information other than the calculation that is there in this chapter, and we've been doing it. You've been witnessing it yourself since we started last week. That there's quite a lot of information that is already in there. Reminding you guys again that this year for grade 11 physical sciences, there's only going to be one paper. We're not going to write two papers like all the other years. So you guys better take advantage of the situation. So you need to take advantage of the situation and make sure that you pass with great marks and great colors, because there's so many things that have been removed. You're not going to even be doing chemical systems this year because of the adjustment. So COVID has, given you guys an advantage, but the main point is to know what you are doing, and that's why we are here. That's why we're pushing this education. I'm reminding you guys again as well that we will be doing assessments soon. And reason why are we doing assessments? We need to do assessments so that you guys can get into the flow of writing assessments and tests, knowing how to manage time during assessments. Those things are very important, and you need to know them as students, because you don't want to get shocked in an exam and you just become jammed because you don't remember how it's like to write or the time setting, etc. So some things you just need to keep your mind at work. Okay, so starting with the homework part. The homework part, we were doing the electromagnetic induction. So these were the questions that came about. Okay, important questions that you guys can use to prepare for your tests and exams as well. So it says a solenoid is connected to a galvanometer that is set on its most sensitive range. Okay, so sensitive range means the galvanometer, remember we spoke about it yesterday. We said it's a measuring device used to measure, to sense electric current. Okay, so here they said it's set on its most sensitive range, so it means it can detect the slightest of electric current flowing on a solenoid. Okay, so describe the effect on the galvanometer needle when, number one, a magnet is pushed into the coil. Number two, the magnet is stationary in the coil. And number three, the magnet is pulled out of the coil. Okay, so let's get to our answer. So it says here, when a magnet is pushed into the coil, the galvanometer deflects. So it shows a non-zero reading, which means there is going to be electric current flowing. Remember, this is part of our definition as well. When a magnet is pushed into the coil, or when stationary coil, when a magnet is pushed into the coil, or when the coil is pushed through in the magnet. Okay, so it could be one of the two. So this is also a definition of electromagnetic induction and how induction takes place. So it will have a non-zero reading. Okay, so it says number two, the magnet is stationary in the coil. Remember what we said in our definition earlier on is that the magnet can be stationary in the coil, but as long as it forms part of the closed circuit of the coil, then there will be electricity that flows. So there will be electric current. So this answer should also be does not deflect, shows a zero reading. Okay, say here the galvano needle does not deflect, it shows a zero reading. Okay, so the magnet is stationary in the coil. Okay, so it means that it's stationary in the coil. So that means they are both stationary. Remember, one of them has to be moving. It's either the coil or the magnet, but one of them has to be moving. Okay, so the magnet is pulled out of the coil. So, okay, but this means that the galvano meter needle deflects, but in the opposite direction compared to question 1.1.1. Okay, so because it's pulled out, which means that it's moving on the opposite direction from the direction that it was moving initially. Okay, so we move to number two, which says briefly describe the results of demonstration 1 in point form. Okay, so it says here, when a conductor and a magnetic field move relative to each other, a current is induced. Remember, I told you one of them has to be moving. Okay, so the voltage induced across the conductor. So if they are stationary relative to each other, no current will be induced. For example, this number 1.2, it says they do not deflect. The galvanometer does not deflect because why? The magnet is stationary in the coil. The coil is also stationary. So there will be no electric current induced. Okay. So there is a like pole at the end of each solenoid where the magnet is being pushed in, and an unlike pole when it is being pulled out. Remember the diagram that we had, guys, where you had a magnet and it showed the coil and it shows the direction of the field that it goes in from one side and comes out from another side. So this is what is explained, that there's a like pole at the end of the solenoid where the magnet is being pushed in, and an unlike pole where it's being pulled out. Okay, in both cases they oppose the motion of the magnet. Okay, so they cut through the magnetic field. Okay, so the magnetic field of the induced current opposes but does not stop the movement of the magnet. Okay, so the magnetic field of the induced current opposes, but it does not stop the movement of the magnet. Why is that, guys? Because the magnet is the mechanism that is releasing the magnetic field. So the induced, as much as it opposes, it doesn't oppose the magnet, it opposes the magnetic field. Okay, it opposes the magnetic field. So you must take note of that. So the induced current, or referred to as EMF, is increased by, number one, moving the magnet faster. So if we move the magnet faster, our induced current would increase, increasing the strength of the magnetic field. In this case, we'd have to put a stronger magnet. Remember, we spoke about this yesterday, increasing the length of the conductor, which means basically the number of turns on the solenoid. So if you increase the number of turns of the solenoid linked with magnetic field, then they will increase the induced current in the circuit. Okay, are we together? So this is basically a short summary of what we are talking about. Okay, so on number 3, it says a learner pushes a bar magnet with its end pole first into a solenoid that is connected to a galvanometer. Draw a diagram to show the magnetic field of the magnet that will be induced poles, and the current in the solenoid. Okay, so let's go to that quickly. So this is how it would look like. Okay, what do they say? Okay, an end pole first into the solenoid that is connected to a galvanometer. Draw the diagram to show the magnetic field of the magnet, which is the magnet that is being pushed into the coil, the induced poles, and the current in the solenoid. So this is how it's going to be. So this is where they say the north pole is being pushed first, and this is our circuit. So this is our induced current. You see, this is our induced current, and then these are our induced poles, and then that is a magnetic field. Okay, are we good to go, guys? Does all of this make sense? Well, I hope it does, because these are things that you guys are going to have to know. Okay, so what they said there is this: you can either put in, if you want to increase the induced current, here's a picture that I can actually explain this. You can either get a stronger or bigger magnet that will increase the induced current, or you see these are the number of turns. You can increase the number of turns, so which means increasing the wire. Basically, you're increasing the number of turns. This will also increase the induced current. And there is a third one. Let me see. Strength of the magnet conductor and moving this magnet faster. So this is the movement of the magnet. If you move it faster, then it can increase the induced current. So guys, this is our homework, and I hope that you guys understood and it makes sense to you guys, and now you understand how the electromagnetic induction occurs, the components that come with it, and how the application of it as well. Remember yesterday we spoke about transformers and generators and how they also use the mechanism of electromagnetic induction. So those are just little things that you guys must also remember for your exam. Okay, so moving on. Today's content, what are we going to be talking about today? Today we are doing Faraday's Law of Induction. Okay, so what are we going to learn? We're going to first learn what is Faraday's Law of Induction. We need to know what is the magnetic field, magnetic flux, another important term. We need to know Faraday's law of electromagnetic induction, and we're also going to do some direction of induced magnetic field. But I'd like us to do this from the Siyavula textbook, because I noticed that it's got quite a lot of explanations. So that's why we have I've chosen to do it in this textbook. Okay, so moving on, we're going to start with Faraday's law of induction. Okay, Faraday's law of induction. So Faraday was a very important scientist in the history of science, as you've always known, and You can hear people talking about it, be it on TV or in books that we read. So, among the discovery of induction, he also transformed his findings from electromagnetic induction into a mathematical relationship. Okay, so before understanding the Faraday's law, we need to be able to measure magnetism. Okay, so these two, they go hand in hand. Okay, so what, okay, these are the terms for magnetism that we need to learn. Okay, so magnetic flux. A magnetic flux, this is a symbol of the magnetic flux, so pronounced as phi. Yes, this sign is pronounced as a phi. So the origin of the word flux means the flow. Okay, the term magnetic flux means the total magnetic field that passes through an area such as a loop. Okay, so the total magnetic field that passes through an area such as a loop. So it is a scalar quantity, and the SI, the standard, the SI unit is Weber. Okay, so this is the definition of a magnetic flux. So you can think of it as the field lines that actually pass through the loop. The field lines that pass through the loop. Okay, so then we have the magnetic flux linkage. This is a similar meaning to magnetic flux. It is linked with a particular object such as a loop or a solenoid. Okay, and then number 3, we have the magnetic flux density, which is a symbol B. This is the measure of the strength and direction of the magnetic field. Okay, is a measure of the strength and direction of the magnetic field. It is a vector quantity, and the SI unit is Tesla, which is T. It is the magnetic flux per square meter of an area that it passes through. Okay, so there we have it. This is 1 Tesla. So moving on, here now we're going to be dealing with relationship between um, the phi and the magnetic flux and the magnetic flux density. Okay, so here is where we're going to go into detail with that relationship. So Faraday discovered that when he moved a magnet near a wire, a voltage was generated across it. If the magnet was held stationary, no voltage was generated. If the voltage only existed while the magnet was moving. So we call this voltage the induced electromotive force, which is the EMF. It's short for electromotive force. Okay, so before we move on to the definition of Faraday's law of electromagnetic induction and examples, we need to spend some time looking at this magnetic flux. What is the real definition of magnetic flux? Magnetic flux is the product of the component of magnetic flux density perpendicular. Please mark this down. The component of magnetic flux density perpendicular to the loop and the area of the loop. Okay, so for a loop of an area A in the presence of a uniform magnetic field B, the magnetic flux is defined as, this is the magnetic flux is equals to the magnetic field times the area and times the angle between the magnetic field B and the normal to the loop area A. So you see, this one is the areas between the two, because remember, it has to be perpendicular. So it becomes perpendicular, then there should be an angle between the two. Okay, so the SI unit for magnetic flux is Weber. I hope I spelled it right. It's Weber. Okay. So you might ask yourself why the angle is included. The flux depends on the magnetic field that passes through the surface. Okay. It depends on the magnetic flux that passes through the surface. So the field parallel to the surface cannot induce current because it does not pass through the surface. So if the magnetic field is not perpendicular to the surface, then there is a component which is perpendicular and the component which is parallel. So the parallel component cannot contribute to the flux. Okay, so hence it's shown here. This is the surface, and this is a magnetic flux. Okay, the magnetic field. This is B. The magnetic field is going up. So you've got two components. You've got one that's going up and one that's going parallel to the surface. So here in this case, this is what we have. This is our perpendicular angle, right? It's got two components. It's got the one that's going up and the one that's going sideways. So if this is our surface that is horizontal like this, it's basically parallel to the B sine theta. So we cannot use B sine theta because it's parallel. What we're going to use is the B cos theta. So this one is our perpendicular component. And that is why we use this component. That's why we have this component into our formula, which is cos B. So it's BA cos theta. Understood, guys? Yes, I hope this makes sense to you guys. So moving on, Faraday's law of electromagnetic induction. Okay, now we get to that. Now that we understand that what happens and the importance of the magnetic flux, which is the product of the component of magnetic flux density, which is what we spoke about, magnetic flux density, perpendicular to the loop or area of the loop, or in other words, you can also say perpendicular to the surface area. Okay, so that's why now we can move to the definition of Faraday's law of electromagnetic induction. So it says here the EMF, which is the electromotive force produced around a loop of conductor, is proportional to the rate of change of the magnetic flux. Okay, so it's proportional to this one. So you see the EMF is proportional to the rate of change of the magnetic flux through the area A of the loop, and this can be stated mathematically. So this is the mathematical time. Okay, so obviously once you see rate of change, you know that it's going to be inversely proportional to time. So the rate of change, which is the time of magnetic flux, which is this one right here. So where the phi is equal to B times A, and B is the strength of the magnetic field, and N is the number of circuit loops a magnetic field is measured in unit Tesla. The minus sign indicates the direction that the induced EMF tends to oppose the change of magnetic flux. Remember, we spoke about it earlier when we did our definitions, that the electromotive force opposes the direction of the magnetic field. So the minus sign can be ignored when calculating magnitudes. Okay, so now we're still on Faraday's law of electromagnetic induction. So now what they say is that Faraday's law relates induced EMF to the rate of change of the flux. Okay, so how do they relate? It means the electromotive force is equals to the change in flux divided by the change in time. So that's what it means. That's how they managed to relate the two, which is the product of the magnetic field and cross-sectional area through which the field line passes. So remember, we said that the flux is equals to BA. So B is the magnetic field and the cross-sectional area is the A. And then we also have the cos theta, right? Through which the field lines pass. So it is not the area of the wire, but the area that encloses, that the wire encloses, okay? So it's not the area of the wire, but the area, the area that the wire encloses that we're talking about in this case. So if you bend the wire into a circle, then the area we would use in a flux calculation is the surface area of the circle, not the wire. Okay? I hope that makes sense. So below, we have an illustration of where the magnet is in the same plane as the circuit loop. So there is our circuit loop right here. And there is our magnet. There would be no current even if the magnets were moved closer or further apart. Okay? There would be no current even if the magnets were moved closer or further apart. This is because the magnetic field lines do not pass through the area enclosed by the loop for an EMF to be induced. Okay? Okay? Oh, yes. So that is it. But I want us to check out something as well. Like I mentioned, that the Siyavula textbook has all the information, has good information with regards to the direction of induced current. So what it says here is that the most important thing to remember is that induced current opposes whatever change is taking place. So if the magnetic field is moving to your right, it will go to your left. So in the first picture, left, there it is, first picture, right, left, this one here. The circuit loop has a south pole of a magnet moving closer. The magnet of the field from the magnet, the magnitude of the field from the magnet is getting larger. The response from the induced EMF will be to try to resist the field towards the pole getting stronger. The field is a vector, so the current will flow in a direction so that the fields due to the current tend to cancel those from the magnet, keeping the resultant field the same. So to resist the change from an approaching south pole from above, the current must result in field lines that move away from the approaching pole. So the induced magnetic field must therefore have field lines that go down on the inside of the loop. So the current direction indicated by the arrow on the circuit loop will achieve this. Test this by using your right hand rule. Put your right thumb in the direction of one of the arrows and notice that the field curls downwards into the area of enclosed by the loop. Okay, so there we have it. Okay, what they were talking about. Okay, so these ones are going downwards. So in the second one, in the second diagram, the south pole is moving away. Okay, here it is. The south pole is moving away. This means that the field from the magnet will be getting weaker. The response from the induced current will set up a magnetic field that adds to the existing one from the magnetic to resist it decreasing its strength. Okay, so another way to think of the same features is just using poles. To resist an approaching south pole, current that is induced creates a field that looks like another south pole on the side of the approaching side pole. So like poles repel, you can think of the current setting up south pole to repel the approaching south pole. So in the second panel, the current sets up the north pole to attract the south pole to stop it moving away. So we can also use the variation of the right-hand rule, putting your finger in the direction of the current to get your thumb to point in the direction of the field lines or the north pole, okay? So we can test all of these on the cases of a north pole moving closer or away or further away from the circuit. From the first case of the north pole approaching, the current will resist change by setting up a field in the opposite direction. So like poles repel, and like we know, common poles, they attract. So alternatively test that putting the fingers on your right hand and the direction of the current leaves your thumb pointing upwards, indicating that it's a north pole, okay? So you see, so now I want us to also check the direction of induced current in a solenoid, okay? So the approach for looking at a direction of a current in a solenoid is the same approach described above, the only difference being that the solenoid, in a solenoid, there are a number of loops of wire, so the magnitude of the induced EMF will be different. The flux will be calculated using the surface area of the solenoid multiplied by the number of loops. So there we have our solenoid. Remember, the direction of current and associated magnetic field can all be found using the right-hand rule. So there it is. So the direction of the current will be such as to oppose change. We would use the setup as in the sketch to do the test. So this is what basically we use: magnetic field moving to the left and the induced current moving according to the right hand rule. So if you see the direction of the field, this is the direction of the current, and if you put your right hand rule, you'll be able to see the direction of the magnetic field. In the case where the north pole is brought towards the solenoid, the current will flow so that the north pole is established at the end of the solenoid closest to the approaching magnet to repel it. Okay, are we good? So in a case like this, in the case where the north pole is moving away from the solenoid, the current will flow so that the south pole is established at the end of the solenoid closest to the receding magnet to attract it. Okay. So in the case where the south pole is moving away from the solenoid, the current will flow so that the north pole is established at the end of the solenoid closest to the receding magnet to attract it. Okay. So this is the one, the north pole. It's slowly attracting the solenoid. And then this one, okay, this one is away from so the south pole is established at the end of the solenoid closest to the receding magnet to attract it. And with this one, the solenoid current will flow so that the north pole is established. Here's the north pole is established at the end of the solenoid closest to the receding magnet to also attract it. Okay, so in this case, in the case where south pole is brought towards the solenoid, the current will flow so that the south pole is established at the end of the solenoid closest to the approaching magnet to repel it. Okay, so these ones are repelling. You can see with the arrows, these arrows are going this way, these ones are going that way, and with this one that we did here, they are attracting each other. Okay, and with this one on top, they also attracting each other. Okay, so that is what I wanted you guys to see with a different direction of magnetic field. Okay, so another thing that I wanted us to do, I wanted us to have our homework for tomorrow. Before we close down this classroom, okay, so this basically, it also explains what we were reading through on the Siavula textbook. It's all about the directions, but you can read through it just to make sure that you understand it properly. So now we move to activity number 1, answers questions on the Faraday's law. So you guys can do all of them. And okay, we're gonna have to, I see, we can do number 2 quickly, which is set Faraday's law in words as an equation. Okay, this, you guys, you can do it on your own because we've already read through it and you know what they are. You know what's magnetic flux, what's magnetic flux density, what's Faraday's law of induction. They are all there. So number 3 says describe the significance, which is the effect of each symbol in the equation for Faraday's law of induction. This one we've also done it, so I don't think you'll have a problem with it. And number 4, explain what theta and b causes that represent in the equation. I just explained this, so I hope that you're not going to have a tough time doing it. And number 4, it says shows a magnet being pushed towards a loop. Okay, remember this is what we're doing now with that other textbook. Is the flux linkage increasing or staying the same or decreasing? Okay. And then number 5 says a current is induced in the loop. Give the direction to the loop of a magnet in an induced current of the induced current. Number 2, describe the effect of the magnetic field of the induced current on the resultant flux linkage with the loop. Number 3, state the direction of the force that the magnetic field of the induced current exerts on the magnet. Okay, so this marks the end of our class, and that is your homework. Please take a picture and do it. The more homework you do, the more you get to understand what you are working with. Okay, so this is the end of our class. Thank you guys so much. My name is Nonkululeko Madondo. I am your physical sciences grade 11 teacher. If you guys do have queries that you'd like to ask from me, you can get me on t33t@gmail.com, and you can send me an email and we can see how we can tackle this physical science of ours that we so dearly love. And thank you guys so much for joining me into this class. This is Africa Teen Geek STEM Digital School, and good day and have a nice day.